All right, let's talk about the secret order of solids. We're going to dive deep into this hidden world, and trust me, it underpins the structure of pretty much everything you see around you.
So let me ask you something. What could a diamond, a snowflake, and a simple grain of salt possibly have in common? I mean, they seem totally different, right? But there's this invisible thread that connects them all. Any guesses?
Okay, the answer? They all share this incredible, deep, internal secret. If you could zoom in, way in, you'd see that their atoms are arranged in these absolutely perfect, repeating patterns. It's this hidden architecture that we're going to unpack today. All right, first things first. In the world of solids, you've basically got two camps. You've got the super organized, and then you have the completely chaotic.
So on one side, you've got your crystalline solids. Look at that beautiful, predictable, grid-like structure. It's just so orderly. And then on the other side, you've got amorphous solids, where the atoms are just a jumbled, random mess. Every single solid out there fits into one of these two families. So let's break that down. A crystalline solid, it's all about that regular and periodic arrangement. It's like soldiers standing in perfect formation. You've seen these everywhere. Think about sugar, the quartz in your watch, even table salt. Now, the complete opposite of that is an amorphous solid. It's all about randomness. There's no pattern, no long-range order to speak of. It's kind of like a crowded room where everyone is just standing wherever they want. Glass and rubber, perfect examples of this atomic chaos. Okay, so for the rest of our time here, we're going to focus on those amazing, perfectly ordered crystalline solids. You gotta wonder, right? How does nature build something so precise? Well, turns out it follows a pretty simple blueprint. It's really just a three-step recipe. Step one, imagine this invisible 3D grid of points just floating in space. That's what we call the lattice. Step two, you choose your building block. This can be one atom or maybe a little group of them. We call that the basis. And finally, step three, you just stick that basis onto every single point of the lattice, and boom, you've got yourself a perfect crystal structure. And this simple formula right here is the absolute key to everything. Lattice plus basis equals crystal structure. That's it. You take the abstract grid, you add the actual atoms, the basis, and what you get is the final ordered solid we can see and touch. Okay, so think about it this way. If the whole crystal is like a giant Lego castle, what do we call the single individual Lego brick that it's built from? Well, that's what we call the unit cell. The unit cell is the smallest little piece, the smallest repeating unit that still has all the information of the whole crystal. It's so cool because if you can understand this one tiny box, you literally understand the entire thing. You just have to imagine it repeating over and over and over again in every direction. But just like with Legos, not all the bricks are the same shape. We have what are called primitive unit cells. These are the simplest ones, with atoms just sitting at the corners. But then you get non-primitive cells. They've still got the corner atoms, but they have extra ones too, like this one here, with an atom plopped right in the middle. And this is where things get really interesting, with this idea of effective atoms per cell. See, in that simple cell, each atom on a corner is actually shared by 8 different cells. So any one cell only really owns 1/8 of that atom. You've got 8 corners, each with 1/8 of an atom, so that's an effective total of just 1 atom per cell. But in the other one, you still have that 1 atom from the corners, plus the whole atom that's sitting right in the center. So that's an effective total of 2. And trust me, that difference between 1 and 2, it's a game changer. Okay, so why should we even care how many effective atoms are in the box? What's the big deal? Well, it all comes down to efficiency. It's about how tightly you can pack those atoms together. And there's a way to measure this. Scientists call it the atomic packing factor, or APF for short. It's really simple. It's just the fraction of space inside that little box that's actually filled up by atoms. It's basically a percentage that tells you how much is stuff versus how much is just empty space. And when you actually look at the numbers, the differences are huge. That simple cubic structure, the primitive one, it's only 52% full. That's almost half empty space. Just wow. But the body-centered one, with that extra atom, it jumps all the way up to 68%. And then there's one called a face-centered cubic. That one gets up to an incredible 74% efficiency. That's literally the tightest you can pack a bunch of identical spheres.
And look, this isn't just some abstract number for a textbook. The APF has a direct impact on a material's real-world properties. It's pretty straightforward. More efficient packing almost always means you're going to get a denser, more stable material. It really matters.
So, okay, we have all these different building blocks, different ways to pack them. It seems like it could get infinitely complex, right? You'd think there would be an endless number of ways to arrange atoms in space. But that's where you'd be wrong.
There are only 14.
That's it, just 14. A French physicist, Auguste Brevet, actually proved mathematically that there are only 14 unique ways to create these 3D lattices. It's incredible. Every single crystal in the entire universe, whether it's ice or iron or a diamond, has to follow one of these 14 master blueprints. That's the only choice. Now, to keep things organized, those 14 lattices are grouped into 7 larger families, which we call crystal systems. And the grouping just depends on the shape of their unit cell box. You've got the perfectly symmetrical cubic system, which we've talked about, all the way down to the least symmetrical one, which is called triclinic.
And here's a perfect example of how that works. That cubic system we've been talking so much about, it actually contains 3 of those 14 revised lattices. Our friends, the simple, the body-centered, and the face-centered structures. See, they all share that same fundamental cubic box shape. They just differ in where the atoms are placed inside it. So when you step back, it's pretty amazing. This secret order of solids, it's all governed by this surprisingly small, elegant set of rules. This deep, hidden architecture is what gives a material all of its properties. And that leads to a really exciting question, doesn't it? If we understand nature's blueprints this well, what happens when we start designing our own atomic patterns? What kind of incredible new materials and technologies could we build from the atom up?